Hello everyone, this is video 14.3. We're going to be looking at ideas of congruence. I mentioned at the beginning of the chapter that we were going to be building toward ideas of symmetry and congruence, and so this is obviously the second of those things. We're going to need a little bit of the transformations that we talked about earlier in the chapter and a little bit of the ideas of symmetry, so make sure you've looked at those sections before you start the video. So let's get started. All right, so we got to be really careful in geometry that we say things are equal. When we're doing algebra or arithmetic, we say things are equal all the time. This just equals that, and we hardly give it a second thought. In geometry, objects are equal if they are literally the same thing. And I don't mean like metaphorically the same thing, I mean literally the same thing. So in this diagram here, we've got two triangles here. We've got triangle PQR, and we've got triangle, so here I'll write this down. So I've got this triangle PQR, and I've also got this triangle SRQ. Now, we'll talk about this a little bit more, but the reason why I'm going in this order is I'm starting here, I'm going along this side, and then going along the middle. So this is my red. And then here I want to be doing the same thing. So I want to go along this parallel side and then along this middle. And so I want to make sure that I'm going in order. We'll talk more about this later, but just in case you're curious why I did them in that specific order. Anyway, so when we look at these two triangles, I can say that RQ is equal to RQ. Why? Because it's literally the same thing. I know that every object is equal to itself. Now, if it's equal, it's also going to be congruent, because congruent just means that they have the same length or the same measure, they have the same attribute. And so I could say that RQ is congruent to RQ. I could also say that PQ is congruent to RS. Now, PQ and RS are congruent because of this object, so they're the same length. I can say PQ is congruent to RS, but I can't say that PQ is equal to RS because they're literally different objects. I could also say, and I should put a little bar over this because these are line segments, I could also say that this angle here, so this angle PRQ is congruent to this angle RQS. So it's these shaded angles here. And so you'll notice I'm doing PQR. I'm describing the segments that are creating this angle, and then RQS to describe that angle there as well. So now I can say that these two angles are congruent to each other. Now, not to get too far into the weeds on this, I could, however, say that the measure of that angle, so if I were to take a protractor and measure those angles, then this would be PRQ, and then the measure of this angle, so however big this is, if I were to measure it, RQS. Now, I could say that these are equal, because now I'm not talking about the angles themselves, which are congruent and different, but the measure, the numerical measure of these angles, which is equal. Oh, I know, it's a lot to take in. The point is, right now, just to be mindful that equal and congruent are not the same thing. If you're talking about numbers, you can probably say that they're equal. If you're talking about objects that are different, then you probably need to be saying congruent. So let's define congruent in some sort of more formalized way here. The book kind of gives two definitions, the first one being a sort of informal definition, when two shapes are the same size and shape, which is pretty informal definition. Although, for the most part, it does the job. The more formal definition is to say that two shapes are congruent if there is a transformation or some combination of transformations which will move one object to the other. So if I've got two objects and I want to show that they're congruent, if I can do some transformation or series of transformations to one object to where its eventual image is the second object, then I know those two things are congruent. So a really basic example here where we've got two rectangles. I suspect they are congruent. I can define that vector, that direction and distance that will move the first rectangle to being exactly where the second rectangle is. And then they'll match up. And so they're congruent. I mean, that's the more formalized, rigorous definition of congruence. If you want to work mostly with this first informal one of just saying the same size and shape, that'll do 95% of the time for what you're going to be teaching. And we'll do a majority of the time in this class as well. I want you to have seen the formalized definition. We'll talk about the formalized definition in class, but from day to day, you can probably get away with using the informal definition most of the time. What we would like to do is be able to define some criteria that will allow us to see if two triangles are in fact congruent right away without having to do a lot of work. And so we're going to limit this discussion in this section to congruence criteria dealing with triangles. Now, the plural is criteria. We're going to look at a lot of criteria. Criterion is the singular, so you'll see here that we're looking at first this side congruence criterion. And what that says is that if I have a triangle with given side lengths, then I know that it's congruent to every other triangle with the same side lengths. So if I've got a triangle that measures 3, 4, 5, it's the same size and shape as every other triangle that has sides of 3, 4, and 5. And I could do those 3, 4, 5 sides in different orders, different rotations, whatever. So if it's oriented differently than the first triangle, then I can use my transformations to sort of reorient that first triangle so that it matches up with the second one. So you can tell here that to make this one match, I would need to do some sort of reflection. So I could flip this triangle over and then rotate it over, and it'll match up with X, Y, Z. You can see that it needs reflection here because the 1, 2, 3 are going like this in the first one, and then going like this in the second one. So they're going in different directions. So I know I need some sort of reflection. So if I were to flip this over this line, then the 3 comes up here, the 1 and the 2, and then slide it over, and it should match up, and we should get the image matching with the second triangle, and that shows the congruence. But again, we don't want to go through all that all the time. So once we recognize that these sides are all the same, then that's sufficient for me to know that these are congruent. Notice this doesn't have anything to do with the angles. We're just seeing that the sides are the same, and so then we know that the two triangles are congruent. Very quickly, we need to talk about this idea of the triangle inequality. And the triangle inequality says that every side of a triangle must have length that is less than the sum of the other two sides. So in other words, for every side A, the length of that side A has to be less than the length of B plus the length of C. Now, I've got two examples here that I wanted to look at. And the first one shows what happens when this isn't the case. And so you can see that we've got this object here with a length of 10 for one side, and then one side of 4 and one side of 5. And if we try to sort of make the 4 and 5 meet, you can see there's a gap there. If they go all the way down to where the 10 is, then you can see there's going to be a gap of 1 unit, whatever units we're using for this. That's never going to make a triangle. That's never, ever, ever going to make a triangle. So this isn't going to work. If we look over here, the second example, we've got this length x. We don't know what it is, but we do know that we have an 8 and we have a 10. So you can see what would happen here if x was, say, 1. If x were 1, then I would get something a lot like this example. I would have a gap here between the 1 and the 8. So that's no good. I want you to also think what would happen if x were 2. So you notice here that it says it has to be less than. It can't be less than or equal to. If x were equal to exactly 2, then that 2 and that 8 would sort of collapse down onto that 10, and they would connect, but we wouldn't get a triangle. We would just get a line. And so x has to be greater than 2, but can't be equal to 2. And the closer it is to 2, sort of the flatter of a triangle we're going to get. And then the bigger it gets, the more of a triangle we're going to get. And yet, x can only get so big. If once it starts to get so big, then we got to start worrying about it forming a triangle with these other two sides. So we know that x has to be greater than 2, but x also has to be less than something. And I'll leave that for you to think about. How big can x get before we run the risk of this becoming not a triangle again? We also have the angle side angle congruence criterion, or ASA congruence. Um, so for this to work, we need to have a side length that is the same for both triangles. And so this length is the same as this length. And we show that by this little mark here. And so then we also need to have the angles that are at the endpoints of those segments to be the same pairwise. Now, the reason I'm saying pairwise is because this pair are equal in measure and this pair are equal in measure. This doesn't mean that all 4 angles have to be the same. It just means that the pairs have to be matching. And so I've got, this is my 1 tick angle, and then these are my 2 tick angles. And so the 1s match and the 2s match. Now, if this is the case, then everything else is going to be of the same length and angle. And so then the triangles will be congruent. You might be thinking, how could that be the case? Well, because no matter what, if I start with this length, and so I've got an acute angle over here, which is my angle 1, and I've got some slightly obtuse angle here, which is my angle 2. So if I'm starting with these 3 parts for every possible triangle like this, then I know that this line is going to continue up, and this line is going to continue up, and they're going to hit at the exact same place, no matter what. And so once we know that these are going to hit in the same place, then I know that this side is going to match this side, and that this side here is going to match this side here. So with these two starting components, these 3 starting components, the 2 angles on the one side, I know I'm going to end up in the same point. I'm going to get the same 3rd vertex, which gives me the same side lengths for the other 2 sides. It also means that I'm going to get this angle to be the same as every one of these angles. We know that anyway because these 3 angles have to add up to 180. So 180 minus these 2 angles is going to be the same as 180 minus these 2 angles, because those 2 angles are the same. So this is how we know we're going to get these triangles to be congruent if we have the angle, the side, and the angle in this orientation. We also have the side angle side, or SAS congruence criterion. And so for this one, it's a lot like ASA, but now I have an angle, which we'll call this 1 tick angle here. And then I need to have the 2 sides that are on the parts of the angle that are formed here. So I got this angle, I need this side coming off the angle and this side coming off the angle. And the same thing here. And I need these lengths to match. And so you can see again, we've got this side with the 1 mark matches this side with the 1 mark. This side with the 2 matches this side with the 2. Now, once I have that, then I know from this angle that this is going to go to the same place. From this angle, I know how long to go, how far to go. So it's going to get me the same place here. And so this length is always going to be the same as this length because these 2 points are always going to be in the same spot relative to our given vertex. And so we know we're going to get all these triangles to match up as well. And so once we know this, then we know these angles match up and so on. I'll erase that because it might get confusing. So this allows us to see, again, that triangles that have this criteria, if you have 2 triangles where we know the angle measure in the 2 triangles and then the sides that are formed on that angle, then those triangles are going to be congruent. Now, you want to really be careful because not every possible way of matching up triangle parts will give us a congruency. AAA, or angle, 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 does not show us that triangles are congruent, and neither does SSA. And I want to take a moment to talk especially about SSA. If all the angles are the same, which is this case here on the bottom, and it's written right there, you can see then that there's nothing that will make the sides to be the same. And we'll talk about this a little bit more coming up when we get into ideas of dilation and similarity. So later on in the chapter, we'll talk a little bit more about this. But hopefully, sort of intuitively, you can see that if all the angles have to be the same, there's nothing that says any of the sides have to be the same length. So that's why this one doesn't work. This first case, though, SSA, is a little more subtle of a reason why it doesn't work. So suppose that we have the side, and the angle, my S, S, and A. And so the point of this diagram here is that I could keep this angle measure, and so I'm going to create this 30-degree angle. So I'll draw it, and then I'll draw this angle, so I know it's going up this way to some point. So there's my angle. Tick. And so I know that this side needs to be 11, so I'm going to mark it off to be 11. So there's this side. Tick. Now, the other side is a 6. And so what happens is there's not a unique position. I could sweep this out using a compass and find that it could go here or it could go here. This side does not have to be in one particular place. And so here, if this triangle uses the larger angle, I could also construct this with the shorter angle. And these 2 triangles have all the same components that are given here. They both have the 6, they both have the 11, they both have the 30 degrees, but we can tell pretty obviously that they're not congruent. There's no way these are the same. I mean, this side length here and this side length here are clearly not the same length. This one's a lot shorter. So SSA is not going to give us triangle congruence. So this last thing is kind of optional, but I wanted to have a look at why we would ever need these triangle congruency criteria and what we could do with them, why they're useful at all. And so I wanted to look at this rhombus here. So if we look at this rhombus, let's draw in this. We're going to ignore this BD for right now and just look at ABC, this big triangle, and then ADC, the triangle on the bottom. Now, one of the things that we know about rhombuses, is that all the sides are the same length. I mean, that's what makes it a rhombus. It's a quadrilateral with all of the sides the same length. So I know that all 4 sides here are all the same length. They're all congruent to each other. Now, I also know that AC is congruent to itself because AC is equal to AC, so therefore it has to be the same length as itself. Now, what this tells me is that triangle ABC and ACD are congruent. Again, not equal because they're different triangles, but I do know that they're congruent. And then once I know that they're congruent, then I know that this angle has to match with this angle. Now, because this is isosceles, because AB and BC are equal to each other in measure, then I know that this angle also equals this angle. and now I know that this angle equals this angle. Now I could do the same thing using BD and using ABD and CBD as my two triangles, and then I get that these are equal to each other as well. So by the same reasoning that I use for the first angles, I can use for the second angles. And so what I get from this is now that I've got angle side angle for all four of these triangles. I know that all of these triangles are congruent to each other. And then once I know that, then I know that these corresponding parts have to all be congruent as well. So this length is the same as this length, and this length is the same as this length. What this tells me is that the diagonals of a rhombus bisect each other, that if I connect the opposite vertices of a rhombus, they'll meet at this center point and they'll cut each other in half. I can also figure out this right angle here that was given. I can show that that's the case. So these properties of various polygons, quadrilaterals or hexagons, pentagons, whatever, I can start to break this down into triangles, use triangle congruency, and start to prove a lot of these properties that you may have seen and may have heard. Now, you don't necessarily need to memorize this property of a rhombus. I just wanted to take a second to show what these triangle congruency postulates allow us to do. So, for your checkpoint problem, I want you to look at this isosceles triangle. The red line that's in the figure there is drawn so that it cuts side BC into two equal parts. And you can see that BD and DC are both drawn with two little marks, so they're shown to be congruent to each other. So what do you know about triangles ADC and ADB? Do we know that they're congruent? If so, how do you know that they're congruent? And then if they are congruent, what else would we know about those two triangles or even about that isosceles triangle? So what else would we know based on all this? So I'll let you think about that. If you have any questions about this problem or any other problem or any other thing from this section, by all means, please bring your question to class and we'll get them answered. All right, thanks.